So in class, when we talked about subspaces, we talked about the concept of span of a set of vectors, which is an important concept that we're going to discuss in a later section. However, another important concept when we're talking about a set of vectors is the idea of linear independence. So that's what this video is about and what we're going to talk about in class tomorrow. So let's give the definition of what we mean by linear independence. So let's say we have a set S that contains vectors from a vector space V. Let's make sure the set's non-empty, because this concept doesn't make any sense about if we don't have a non-empty set. So we say that S is a linearly independent subset of V if you have a linear combination of the vectors from S that give you the zero vector, then you necessarily had to use zeros for your constants. Certainly if I use zeros for the constants, I'll get a linear combination that gives me the zero vector. However, it's possible for in other scenarios where you could see using different constants that would still give you the zero vector. For example, if you had the vectors 1, 0, and 2, 0, you could take -2 times the 1, 0 vector and add it to the 2, 0 vector, and you'll get 0, 0. That would be a linear combination that gives you the zero vector that did not involve using all zeros as your constant. Said another way for this definition, when we say we have a linearly independent set of vectors, we're saying that the only linear combination that can give you the zero vector is using all zeros. Certainly all zeros always works. What we're saying if it's linearly independent is it's the only way that you can do it. And the third way to think about linear independence is that if they're not linearly independent, then you can write one of the vectors in terms of the other ones. Well, what that really means is that the vector that you can write in terms of the other ones is just unnecessary information. And we'll talk about that more later in a later section in class. Anyway, for the purposes of this video, I just want to show you how you can show a set of vectors is linearly independent. So let's start with an example. Let's say we have the vectors 2, 5, 3, -1, 6, 2, and 1, 0, 3 is a subset of three vectors in R3. I want to see whether or not these vectors are linearly independent. So to start that, let's suppose that we have constants C1, C2, and C3, so that when I take that linear combination of those three vectors, I get the zero vector. And the zero vector in R3, of course, is 0, 0, 0. Well, if we start equating components, we can get a system of linear equations. What I mean is, if we actually do the scalar multiplication and do the addition here, and equate components, we get a system of equations. So in this particular case, we would get 2c1 minus c2 plus c3 equals 0. That's coming from the first components of the vector. We get 5c1 plus 6c2 equals 0. That's coming from the second components. And then likewise, the 3c1 plus 2c2 plus 3c3 equals 0 is coming from the third components. We know how to solve systems of equations like this. We can put it in a matrix and row reduce. So if we do that, in this case, put it in a matrix, row reduce, we get the identity matrix and then augmented with a set of zeros here. Notice that this gives us only the trivial solution because it says C1 had to be 0, C2 had to be 0, C3 had to be 0. Therefore, if we have a linear combination that gives us the zero vector, we have to have those constants really were 0. So that tells us that the set is linearly independent. Let's do another example that are from a different vector space. It's not just one of our Euclidean vector spaces. Let's say we have a set of these four polynomials from P3. So we've got the polynomials 5 plus x minus x squared plus 3x cubed, 2 plus x squared minus x cubed, -3 plus x plus 2x squared, and then 5 plus x minus 8x squared plus 10x cubed. So we got the set of four polynomials from P3. Remember again, P3 is our set of polynomials that have degree 3 or less, along with a zero polynomial. We want to see whether or not this is linearly independent. So we set it up the same way we set up the previous one. We want constants. In this case, we need four constants because we have four vectors in our set. We just have the constant C1 times the first polynomial plus C2 times the second, C3 times the third, C4 times the fourth. We want that to be equal to 0. Now in the previous example, we equated components. In this example, since we have polynomials, we'll equate like terms. Notice on the right-hand side, we have 0 constant term, 0x term, 0x squared term, 0x cubed term. So we're just going to equate like terms. So Equating your constant terms, you get a 5c1, a 2c2, a minus c3, a 3c3, and a plus 5c4. When we add those together, we have to get 0. Likewise, the second equation comes from equating x terms, the coefficients on the x terms. The third equation is coming from equating the coefficients on the x squared terms. And the last equation is from equating coefficients on the x cubed terms. Again, we have a system of linear equations. We know how to solve these. Put it in a matrix and row reduce. In this case, when we row reduce, we don't see that nice ones down the diagonal, right? We've got this free variable on the right-hand side. So what does that tell us about the system of solutions? Or the solution to the system, I mean. Well, when we have a free variable, we get infinitely many solutions. In fact, for any number t that we pick, we can figure out what the solutions are. This gives us a linear combination that gives us 0. So what we mean is, so for example, if I get -2 for C1, 4 for C2, 1 for C3, and 1 for C4, if we do that addition, we will get 0. You can check that, but you will get 0. That means that we can use non-zero scalars, at least one non-zero scalar, but we can use non-zero scalars to give us a linear combination that gives us the 0 vector, which is just the 0 polynomial in P3. That means the set is not linearly independent, or in other words, we would say it's linearly dependent. What you should go back and do before I go on to the next slide is go back and look at the correspondence to how we formed the matrix and the corresponding vectors in the vector space. And what I mean is, just looking at the left hand, to the left of the augmentation bar here, look at these coefficients in this example, or the entries in this matrix in this example and the previous example, and see how they compare to the vectors that we're trying to check whether or not they're linearly independent. Okay, we're going to discuss that more in class, but see if you can figure out the relationship between those. All right, so to give you one more idea of why we care about linearly independence, let's say we have a linearly independent subset. If we have a linearly independent subset, let's say we have two ways that we can write a vector v in a vector space. So what I mean is, let's say I have two different linear combinations of these vectors in the set. So this is a linear combination of the x's. This is also a linear combination of the x's. Let's say we have two linear combinations that give me the same vector. Well, if we subtract the two equations, certainly when we subtract the right-hand sides, we get 0. When we subtract the left-hand sides, we can factor out the x's in each of the terms, if you will, and get this. Well, we know that this set x1, x2 out to xn is linearly independent. That forces these coefficients to be 0. If that forces these coefficients to be 0, what does that mean? Well, if they're 0, then that means that C1 had to be D1, C2 had to be D2, and so on down the line. That means that if we have two linear combinations that give me V, they're actually the same exact linear combination. So what that means is that if a vector is expressible as a linear combination, that linear combination has to be unique. That means we get unique representation of these vectors by vectors in our linearly independent set. That's going to be an important concept later on, so keep that in mind. When we have a linear combination of linearly independent vectors, that's the only vector that you can get from that linear combination. What I mean is, if I have that vector, there's no other linear combination that gives me the same vector unless I use the exact same linear combination. So that concept's going to pop up later. So hopefully this gives you an idea of how to check for linear independence. We'll talk about more of the conceptual stuff in class.